Hello guys, good morning. Welcome to the KPI session of chemistry. So last class we discussed about Sn2 reaction. We have seen few examples of Sn2 reactions. Now in the same series we are going to discuss the next nucleophilic substitution reaction, that is Sn1. Basics of Sn1 I have already discussed. Okay, I have already shared the video, uploaded the video of Sn1 reaction, how the mechanism goes, and number of steps involved, formation of carbocations, those things I have already discussed. Okay, so in this section mainly we'll cover those reactions which is based upon Sn1 reaction, right? And few more things we'll discuss into it. Correct? So let's start with the session. So a brief recap of Sn1 reaction. Sn1 reaction we have discussed. In the substrate, we have a leaving group, that is RL, leaving group, and we have a nucleophile. This nucleophile could be moderate, not very strong. Okay, this nucleophile is not very strong. Okay, so when it goes under reaction, right, so it gives product that is RNU, and the leaving group goes out, L minus. Okay, the steps involved in this, if you see the mechanism part of it, the first step is the formation of carbocation. The RL, the bond dissociates, forms a carbocation, and the leaving group goes out. Okay, and in the second step, this R plus carbocation is get attacked by the nucleophile Nu minus, and it forms RNU. This is the reaction. We have whole mechanism. Okay, this step is what? It is the slowest step, and it is the RDS of the reaction. Okay, and that is why I have already discussed this thing. The rate of this reaction is directly proportional to the stability of carbocation. Stability of carbocation. We have other factors also, but this one is the most important one. Okay, okay, since carbocation is forming, so this substrate must be tertiary, because tertiary carbocation is stable. See, I have written over here tertiary, but it does not mean that it is only tertiary. Okay, we can have other compounds also, which gives a stable carbocation, right? So that is what important we have here. If the possibility of getting a stable carbocation, then it may go under Sn1 mechanism. Okay, so tertiary I'm writing down with respect to primary, secondary, or tertiary. If you have, then tertiary is preferred for Sn1 type reaction. Primary is preferred for Sn2 type reaction. So if you have alkyl group, in general, if I write down, if you have alkyl group attached to the leaving group, right, it may be 3 degree, it may be 2 degree, it may be 1 degree, right? Or we can have methyl that may also attach to the leaving group we have. So in all these cases, you see, in all these cases, if you go from methyl to tertiary like this, and if you go from tertiary to methyl like this is the two possibility we have, right? So methyl to tertiary, if you go methyl to tertiary, if you go like this, then chance of Sn1 mechanism is more over here. So here we have Sn1 reaction increases, and this side we have Sn2 reaction increases. Tendency to go under Sn1 increases, tendency to go under Sn2 increases. Okay, these are the points you must keep in mind. Now some basic example we see. The first example you see, we have, suppose, a carbon attached with 3 methyl group, CH3, CH3, CH3 and Cl. Leaving group is chlorine, and it is allowed to react with ROH, alcohol. The product of this reaction would be, this would be as it is. We have here OR and we get HCl. This is CH3, this is CH3, and this is CH3. How does this reaction goes, you see? First of all, this gives us a carbocation, which is a tertiary carbocation, which is this CH3, 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 and positive charge plus Cl minus goes out, right? And this again reacts with the leaving the nucleophile here, which is ROH. This is a nucleophile. It has lone pair present on the oxygen atom, behaves as a nucleophile, and this attacks on the carbon atom, the positive charge carbon atom, right? And it converts into carbon with CH3, 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 and this get attached with OR here, and H plus comes out from this. Okay, this H plus combines with Cl minus and converts into HCl. This is the mechanism we have, and the product. Okay, so this step, if you see, this step is the RDS, formation of carbocation. It is the slow step, slow and RDS of the reaction. Okay, like this the reaction goes. So this is what it is, Sn1 mechanism. This mechanism is Sn1 we are discussing here, right? Now in this only, suppose we have the next thing. If you take here, suppose I'm taking 1 degree alkyl halide here, that is CH3 CH2 Cl, and this reacts with ROH, right? This also forms CH3 CH2 OR plus HCl. The product you see, one step if you see, it looks very similar, right? But the mechanism is different here. Here the mechanism is Sn2. Why? Because it is 1 degree alkyl halide primary, right? 1 degree alkyl halide primary, right? Preferably for 1 degree alkyl halide, we take a strong nucleophile. Means if you take this one, only possible reaction is this. Sn1 reaction is very difficult to proceed here. But what we preferred here, we preferred stronger nucleophile, stronger base. Means for this one, if you take RO minus, then the rate of reaction, when you take RO minus, it would be more. With this nucleophile, we have more rate of reaction, right? That's why this is preferred. This one is preferred. But the case is not this. Okay, the case we have this one. The reaction is with ROH. Okay, so with ROH, you will have Sn2 only possible because the 1 degree alkyl, right? Okay, and the possible reaction is this, right? So it's simple. We have inversion takes place, it attacks from the back side, and Cl minus goes out. Okay, so this is one small comparison of Sn1 and Sn2 reaction. Okay, another example you see, we are mainly focusing on Sn1 reaction here. The second reaction you see, that is suppose we have pH CH2 Br, with H2O, right? It forms pH CH2OH alcohol. Okay, I'm going pretty slow here because it's difficult for 11th graders to understand these things at this level. Okay, so if you get 50% of it, you will have an idea in the exam that what could be the possible product, right? It's always better to get something, rather than leaving it completely, right? So that's the thing. Okay, something like it's always better than nothing. Okay, so if you get 10%, 50% of it, that is fine. Okay, if you revise this twice or thrice, you will be understanding it in a proper way, right? So for organic chemistry, the revision is required. Continuous revision is required. Okay, now this mechanism you see here, this mechanism is Sn1, right? This mechanism is Sn1. Why it is Sn1? Because this molecule you see here, the molecule that we have, pH is the phenyl ring, that is the benzene ring we have, right? This is the benzene ring, and on the benzene ring we have CH2 and Br. CH2 and Br. Okay, so if this goes out, if this Br minus goes out as a leaving group, this is the slow step, then it forms a carbocation, which is this, that is CH2 plus plus Br minus. Okay, and this carbocation is resonance stabilized. Okay, so we have discussed resonance already. It is resonance stabilized, hence it is a stable carbocation and it can form in this reaction, and that is why the path of the reaction is Sn1. Okay, so once you get this on this, there will be an attack of nucleophile, that is H2O. H2O will attack on this, and it eventually converts into OH here, that is CH2 OH, and H plus goes out. This H plus combines with Br minus and forms HBr. Okay, so here in the next step, here we have the attack of nucleophile, that is H2O, and it forms this molecule. Got it? Few more examples I'll show you. See this example. Suppose you have Cl here, right? And it is allowed to react with H2O. So here also the chlorine is a leaving group. It gets replaced by OH, forms this. And this mechanism is Sn1 mechanism again. Why Sn1? I'll show you. See what happens in the first step. In the first step, this converts into the leaving group goes out, and this converts into a carbocation, which is this, right? This is the RDS, slow step of the reaction. Carbocation forms. And why this carbocation is forming? Because this carbocation is also resonance stabilized here because of this. It is in conjugation, pi sigma lone pair, right? So here also resonance possible here with this carbocation, hence it is stable and it forms in the reaction. So in the next step, H2O behaves as a nucleophile. H2O behaves as a nucleophile, and this attacks onto the carbocation, right? And it converts into OH. I'm just explaining this particular step also here. Since oxygen donates its lone pair, so oxygen will have positive charge on this. Okay. Now to stabilize this positive charge, one H plus comes out, right? Negative of H plus, so that this leaves this electron pair behind on this oxygen. So it converts into this molecule, plus H plus, and we have OH here. So this is the product we get. In fact, in all those reactions, the reactions goes this way only. Okay, H2O attacks, alcohol attacks, then oxygen have positive charge. To stabilize the positive charge, the H plus comes out and it forms the product, that is the final product. Okay, fine. One very important reaction we have, that is the dehydration of alcohol. Dehydration of alcohol. Okay, alcohol dehydration means removal of water. Sorry, not dehydration, it is hydration of alcohol, my bad. Dehydration means removal of water, and it becomes elimination reaction, okay, which is the next part we'll discuss later. But here we are talking about hydration of alcohol. Hydration means what? It is basically acidic hydrolysis. It is acidic hydrolysis of alcohol. Hydrolysis means dissolution in water, to dissolve in water. Acidic hydrolysis means in presence of acid, dissolution of alcohol into water. Okay, this reaction this reaction follows Sn1 mechanism. Sn1 mechanism. How the reaction proceeds, you see here. Suppose I'll take the simplest one, the simplest example. Suppose we have CH3 CH2 OH reaction with water in presence of an acid. So we can take dilute H2SO4, right? So what happens here, you see, this gives H plus. How the mechanism goes, I'll show you. This gives, first of all, I'll show you the okay, I'll make one change over here because it will give the same product. The change is okay, we'll take CH3 CH2 CH2OH. We are going to understand a different concept here. Okay, so what happens here, you see this acid, it gives what? It gives H plus, and that is the definition of an acid, which increases the concentration of H plus ion in the aqueous solution. This is an acid will give H plus from here. This lone pair on this oxygen, it gets protonates and it accepts the H plus that comes from the acid. This is the protonation. We call it as protonation of this group. Okay, so it converts into what? This converts into CH3 CH2 CH2O. One hydrogen we already have, another one comes from acid and a positive charge on this oxygen. Okay, so in the next step, you see this comes out as water molecule because oxygen is an electronegative element. The positive charge on oxygen is not at all stable. To stabilize this, it drags the electron pair and the bond dissociates between the carbon and oxygen. It forms CH3 CH2 CH2 positive, that is carbocation, and H2O molecule goes out. Okay, I'm giving you one different concept here. This carbocation is 1 degree carbocation, primary carbocation. Okay, this forms in the first step. And whenever carbocation forms in Sn1 reaction, the rearrangement of carbocation possible. Listen to me very carefully here. Rearrangement of carbocation possible means if there is any possibility to get more stable carbocation, we'll definitely do that. Okay. Now there are different methods to get the more stable carbocation, right? We'll have ring expansion, ring contraction, okay, phenyl shift, hydride shift, methyl shift, aromaticity, if it is gaining. So there are many different methods we have. But here we are not going to do ring expansion and all, right? Because it is for KBY. So we'll just focus on the basic concept of it. Okay, so what happens, you see here, we have one carbocation, which is this, right? And we'll try to get the another carbocation, and we'll see whether it is stable or not. See, we have one hydrogen present at this alpha position, right? So what happens in the reaction? It happens on its own. It's not like we are doing anything into it, right? It happens on its own that this hydrogen from the adjacent carbon, we can have hydrogen, we can have methyl, we can have phenyl here, right? So these hydrogen atoms, since we have hydrogen here, I'm talking about hydrogen, it takes the electron pair, the sigma electron it takes, and it migrates itself onto this carbon atom. This is migration here. It takes the electron and it shifts onto this carbon atom. This we call it as 1,2 hydride shift. Because hydrogen atom is getting displaced, getting shift, right? So it is hydride shift. If it is methyl here, then methyl shift. I will show you that example, the next one. Okay, 1, 2, 1, 2 hydride shift we have here, first, second position. Okay, and this number is nothing that is not related with the IUPAC nomenclature, the numbering over there. It's not related with that. Just first and second carbon, the shifting is taking place. So 1, 2 hydride shift. Now, what happens with this shifting you see here? See, when this hydrogen shift over there, right? So this molecule, it becomes CH3, CH3, one hydrogen comes over here. And since the carbon, here you see, the 2 electron we have here, right? One for carbon, one for hydrogen. Hydrogen takes both the electron and it migrates onto this carbon. Means carbon loses its electron. The electron of carbon is taken up by hydrogen and it migrates onto this carbon atom. Hence, this carbon has one positive charge since it loses one electron. Simply you can understand, hydrogen shift over here, this carbon will have positive, this carbon will have the hydrogen like this. Okay. Now, if you compare the stability of this one and this one, first of all, the second one, it becomes 2-degree carbocation, which is obviously more stable. We know that. But if you look at the stability of this carbocation through hyperconjugation, we have alpha hydrogen, that is 2 here. And here, if you count alpha hydrogen, it is 6. So obviously, it is far more stable than this one. That is why in the reaction, this carbocation converts into this. By this shifting, this arrangement. And this arrangement happens on its own. If you do not do it on the paper, but actual reaction if you do, there will be rearrangement and you'll get the product according to the most possible stable carbocation that can form in the given compound. Got it? So this is the most possible stable carbocation we have. And then it converts into, we have the attack of a nucleophile, and nucleophile is water here. Water molecule is behaving as a nucleophile, the attacking particle. So this is a lone pair, and this lone pair, it attacks onto this carbon atom, right? And then H2O plus, H plus goes out, we'll get OH over here. So the final product of this reaction is CH3, CH, CH3, and OH here. Finally, you'll get 2-degree alcohol. So the product of this reaction, this is the mechanism I have discussed. The product of this reaction is this one. See the bond line is structured. This is the product we have. Okay, so this kind of shifting, hydride shift, if you have methyl group, then methyl shift, phenyl group, then phenyl shift, it is possible in Sn1 mechanism. In Sn2, this kind of shifting is not possible because we know in Sn2 there is no carbocation formation. Carbocation won't form in that reaction. Okay, some more example on this type I'll show you so that you will have a better understanding of it. Suppose the second molecule I'm taking, and that is CH3, CH3 and CH2OH. And directly if I write down the reaction, we have H plus H2, acidic hydrolysis. H plus means acid here. Okay, then the product here we get is, I'll write down the product, then I'll show you the mechanism. CH3, CH3. Here we get CH3 and here we get OH. This is the product we get. Plus we'll have the H2O molecule. Okay, how the reaction proceeds, you see. The first step of the reaction is the protonation of hydroxy group. This one. This gets protonates. It takes H plus from the acid, right? And it gets protonated, so it forms CH3CH, CH3CH2. Oxygen has 2 hydrogen positive charge on it. Okay, and then in the next step, what happens? In the next step, removal of water. How it happens? It takes this bond pair of electron, because oxygen again has 1 positive charge, not stable, and it converts into CH3, CH, CH3, CH2 plus H2O. Okay, now next one is the attack of is the carbocation forms. Now this carbocation, you see, it is 1 degree carbocation. Is there any possibility to get more stable carbocation? Let's check that. Okay, so we can think of shifting this hydrogen here and this methyl here. Let's check the both case, what happens in this. Okay, so both case we are considering here, the shifting of methyl plus the shifting of hydrogen. So both case, if you see, one of the case is this, right on this side, another one is this. Okay, suppose here we have hydride shift. Here we have, suppose, hydride shift. This comes over here. Right. So this red one represents hydride shift. So I'll just make a change over here so that there won't be any confusion. I'm taking 2 different color so that we can understand it properly. So this shift is the red one, and red one gives you this. Okay, so what happens with this red shift, you see? We get here a new carbocation, which is CH3, C positive charge, CH3, CH3, positive charge on it. With this orange color, you see what happens with orange color. If I'm considering the shifting of this methyl group here, like this, suppose. Shifting of methyl group. So orange shift gives you what? Orange shift gives you this molecule, which is CH3, CH, positive charge, CH2, and here we have 1 methyl group which gets shifted over here. These are 2 possibility, right? So the one which gives more stable carbocation, that will take this. Okay, so this is, we call it as the orange one, 1, 2. It is methyl shift because CH3 is getting the shift. Hence it is methyl. Okay. If you have hydride shift, this we call it as 1, 2 hydride shift. Hydride shift. Okay. Now, when you look at the stability of these two carbocation, let's compare that with the help of GOC. It is stabilized through hyperconjugation, and its alpha hydrogen is 5 here. And for this, the alpha hydrogen is 3 plus 3 plus 3, that is 9. Hence, this one is more stable and this forms in the reaction. This is not more stable. Obviously, it's stable than this. This one is more stable than this, right? Because it has only one alpha hydrogen. Alpha hydrogen is 1 here. So obviously, these two carbocations are more stable than this. Okay. If you see, this is 3-degree carbocation and this is 2-degree carbocation. Again, we know 3 degree more than 1 degree, more stable than 1 degree. But since this carbocation is more stable, hence this won't take place. Okay, so it will be either this or this depending upon the stability. Okay, so I have just written here to make you understand the stability of the two, right? So this is not possible in this one. We won't do this. This is more stable. So hydrogen will shift here and we'll get this carbocation. And the last step, this carbocation is getting attacked by the nucleophile, and that is water here. So I'll write down the product directly. That would be CH3, 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 and OH here on the top. This is the final answer for this question. Okay, so this kind of shifting takes place in Sn1 reaction, not in Sn2. Okay, I hope you get it. Okay, next example in this. Suppose we have an example CH3, C, CH3, CH3, CH2, CH2, OH. This goes under acidic hydrolysis, H plus H2. Okay, acidic hydrolysis. Okay, so we'll see the reaction here, what happens. So first of all, there will be the protonation of oxygen with the help of H plus of the acid. Okay, this one will take this H plus and it forms what? It forms H2O. H2O goes out and we'll get this. That is CH3, CH3 on the top, CH3 on the bottom, CH2, CH2 positive charge on it. Okay, plus H2. Right? Now in this, we'll have 1,2 hydride shift. H here, and we are considering 1,2 hydride shift on this. Okay, so that would be the product we get here, you see. The product we get, it is CH3, 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 CH positive and CH3. If you compare the stability of this one, it is 1 degree, alpha hydrogen is 2, 1 degree carbocation. This one is 2 degree carbocation, alpha hydrogen is 3 here, right? So obviously this one is more stable than this, so this will form in the reaction. But this is actually not the most stable one. We can have further shifting possible. Further shifting possible. And what happens here? This one of the methyl group takes the bond pair of electron and shift onto this positive charge adjacent carbon. Okay, so this converts into CH3, CH3 this side, CH3 this side. Here we have CH3 and a positive charge on the carbon atom. Okay, now if you compare the stability of this carbon atom, it is 3 degree, right? Alpha hydrogen is what? 3 plus 3 plus 1, that is 7. So obviously this carbocation is more stable, right? So this one was 1,2 hydride shift, and this one is 1,2 methyl shift. Okay, so this kind of multiple shifting is possible in a molecule. The objective is to get more stable carbocation in each step. After each shifting, you should get more stable carbocation, right? Each shifting, you should get more stable carbocation, then only it's possible, right? Further, if you shift, suppose if methyl, let us understand this. Suppose you can say, so why not one more hydrogen shifts over here, right? So let us try and understand this also. Further, I'm considering the methyl shift. Okay, so I'll just change the color here. Further, if one more methyl hydride shift, if you consider here at 1,2 hydride shift. So what happens? This is H2 and this is H. And if you consider the shift here from this to this carbon, right? What happens, you see? We get here CH2 positive charge. Then we have CH, CH3, CH, CH3, and then we have CH3. Okay, we'll do this. Now, if you consider this, again, it becomes 1 degree carbocation, and alpha hydrogen for this carbocation is only 1. Right? So this one is not stable in comparison to this. So reaction won't go from a more stable carbocation to a less stable carbocation, right? Hence, this reaction, this step is not possible, right? This won't form and step is not possible. So there will be shifting 1,2. It's not like from this position to this point. It's not possible like that. One by one you go, stepwise. Adjacent carbon. Shifting always takes place from adjacent carbon. Okay. So, and the objective is in each step, you should get more stable carbocation. Like you see, this has 2 alpha hydrogen, this has 3 alpha hydrogen. So this shifting is possible, right? This one is correct. This to this, again, 7 alpha hydrogen, more stable than the previous one. This is also possible, right? So in any step, if the carbocation stability is not increasing, then that particular step is not possible. no matter if you're having a possibility of getting more stable carbocation in the next step. That doesn't matter. If this to this stability is not increasing, it is not possible. As simple as that. Okay. So the only molecule is this, which is, I'll just remove this. This thing is not possible. So this is the carbocation we get here, most stable carbocation. And on this carbocation, in the last step, H2O behaves as a nucleophile, attacks on this, and finally we get OH over here. The product is CH3, COH, CH3, CH, CH3, and CH3 here. So this is the final answer we have in this question. So this kind of multiple shifting, more than one shifting, is also possible in the reaction. That is the hydration of alcohol. Acidic hydration. Acidic hydration means what? Dissolution of alcohol into water in presence of an acid. Okay, that is acidic hydration. Okay, fine. One last thing of Sn1 reaction we'll discuss here. There is a test here, right? There is a test, sorry. The test is Lucas test. Lucas test. We use to differentiate, write down, it is used to differentiate primary, secondary, and tertiary alcohol. Primary, secondary, and tertiary alcohol. Right? And for this purpose, we use a reagent that we call it as Lucas reagent. Sometimes in the exam, they also ask, what is Lucas reagent? So Lucas reagent is ZnCl2 plus HCl. And this is concentrated HCl. ZnCl2 plus concentrated HCl. Okay. Now what happens in this reaction, you see? This reaction is obviously the acidic medium reaction we have. Okay. So when you have alcohol, suppose ROH, OH alcohol we have, when it is allowed to react with HCl in presence of ZnCl2, okay, it converts into RCl, and there will be a turbidity that appears here. Turbidity appears here. Okay, so how this reaction proceeds, you see. This acid gives HCl here because when these two reacts, I'll write down. It goes this way. When these two reacts, HCl and ZnCl2, it forms H plus and ZnCl3 minus. This H plus, it actually reacts with alcohol here. It protonates the alcohol, the same thing we have for alcohol. It protonates this and it forms OH, H positive charge on it. And then there will be elimination of water molecule. It converts into R plus H2O. Right? Now, Then from this, ZnCl3 minus, Cl minus comes out from ZnCl3. I'll write down here in the bracket. From ZnCl3 minus, Cl minus comes out, and this attacks onto this carbocation, right? And it forms RCl finally. Okay, so this step now here, what is Sn1? Because it is Sn1 reaction, I told you. So this step is the formation of carbocation. This is the slowest step. Sn1 reaction is this one, right? So depending upon the alcohol, this can be right. I'll write down here, depending upon the alcohol, carbocation could be 1 degree, 2 degree, or 3 degree. We know 3 degree carbocation is most stable. So rate of reaction is, we know it is maximum for 3 degree, then 2 degree, and then 1 degree. Okay. So this turbidity that appears, that white turbidity or the cloudiness that appears, right? If this turbidity appears very quickly, like within seconds, it means the rate of the reaction is very fast. And that possibly gives tertiary alcohol, right? Because we know tertiary alcohol, suppose you have a compound that you need to test, whether it is 1 degree, 2 degree, or 3 degree. You put this into this thing. Like suppose you have 3 compounds, one is 1 degree, other one is 2 degree, other one is 3 degree alcohol. And you do not know which one is 1 degree, which one is 2 degree, 3 degree. It's simply given, right? The structure is not given, you just have it. Okay. You can't see this there in the box fixed, right? So if you one by one, if you place these compounds into the solution, right, it gives turbidity, right? So depending upon the time taken for this turbidity to appear, we can say whether the compound is 1 degree, 2 degree, or 3 degree, because we know the rate of the reaction with respect to 1 degree, 2 degree, and 3 degree. Okay. So if turbidity appears very fast, right, then it is tertiary within seconds. It is secondary. It is tertiary. If turbidity appears in minutes, right, that is secondary. If it take hours, then it is primary. And primary does not go under Sn1, that would prefer to go under Sn2 reaction. So let us see this table here. Okay. See, here we have substrate, and it is the time taken for the turbidity to appears. Right, time taken for the turbidity to appears. If it is 1 degree substrate, 2 degree, or 3 degree. If it is 3 degree, the time, then the turbidity appears in seconds, it takes minutes, and it takes hours. Okay, so depending upon the time taken for turbidity to appear, we can differentiate whether the alcohol is 1 degree, 2 degree, or 3 degree. If it is Sn2 mechanism, sorry, if it is 1 degree alcohol, then it preferably follows Sn2 mechanism. It won't follow Sn1, that you must take care of. Okay, in general, this is the reaction we have. Okay, so this is the Lucas test. Okay, Lucas test, sometimes they have asked this question that Lucas test is used for which compound. So it is used to differentiate alcohol. Okay, it is used to differentiate primary, secondary, and tertiary alcohol. This is very important. Okay, Lucas test. Okay, so Lucas test, depending upon the alcohol, it can show Sn1 or Sn2 mechanism. That's a very common understanding we have, that depending upon the the molecule structure, whether it is 1 degree, 2 degree, or 3 degree, the mechanism of the reaction would be correct. So this is it for today. We are done with Sn1 reaction. Okay, so you can solve few questions based on this. However, you won't get a separate PDF or the questions for Sn1, Sn2. You'll get a mixed question into that, but we'll have the discussion of that also in problem solving session. Okay, thank you, take care, bye bye.